In the previous video, we saw how to use a thread in a subclass. Welcome to the fourth video of this section, Thread Synchronization with Lock. In this video, we'll see how to manage a thread through the mechanism of lock parentheses. So let's begin with thread synchronization with lock. When two or more operations belonging to concurrent threads try to access the shared memory and at least one of them has the power to change the status of the data without a proper synchronization mechanism, a race condition can occur and it can produce invalid code execution and bugs and unexpected behavior. The easiest way to get around the race condition is the use of a lock. The operation of a lock is simple. When a thread wants to access a portion of shared memory, it must necessarily acquire a lock on that portion prior to using it. In addition to this, after completing its operation, the thread must release the lock that was previously obtained so that a portion of the shared memory is available for any other thread that wants to use it. In this way, it is evident that the impossibility of incurring races is critical, as the need of the lock for the thread requires that at a given instant, only a given thread can use this part of the shared memory. Despite their simplicity, the use of a lock works. However, in practice, we can see how this approach can often lead the execution to a bad situation of deadlock. A deadlock occurs due to the acquisition of a lock from different threads. It's impossible to proceed with the execution of operations since the various locks between them block access to the resources. For the sake of simplicity, let's think of a situation as shown in the figure wherein there are two concurrent threads, thread A and thread B, who have at their disposal resources 1 and 2. Suppose thread A requires resource 1 and thread B requires resource 2. In this case, both threads require their own lock, and up to this point everything proceeds smoothly. Imagine, however, that subsequently before releasing the lock, thread A requires a lock on resource 2 and thread B requires a lock on resource 1, which is now necessary for both the processes. Since both resources are locked, the two threads are blocked and waiting for each other until the occupied resource is released. The situation is the most emblematic example of the occurrence of a deadlock situation. As said, therefore, showing the use of locks to ensure synchronization so that you can access the shared memory on one hand is a working solution, but on the other hand, it is potentially destructive in certain cases. Lock allows us to restrict the access of a shared resource to a single thread or a single type of thread at that time. Before accessing the shared resource of the program, the thread must acquire the lock and must then allow any other threads access to the same resource. The code which we can see demonstrates how you can manage a thread through the mechanism of lock. In this code, we have two functions, increment and decrement respectively. The first function increments the value of the shared resource, while the second function decrements the value, where each function is inserted in a suitable thread. In addition to this, each function has a loop in which the increase or decrease is repeated. We want to make sure, through the proper management of the shared resources, that the result of the execution is equal to the value of the shared variable that is initialized to 0. The sample code is shown here, where each feature within the sample code is properly commented. In the main method, we have the procedures which are shown here. For thread starting, use this. For thread joining, use this. In the increment with lock and decrement with lock functions, you can see how to use lock management. When you need to access the resource, call acquire method to hold the lock. This will wait for the lock to be released if necessary, and call release method to release it. Now let us run the code and see the output. Go to your command prompt and navigate to your working directory and run the Python file. As you can see, we have the correct result with the appropriate management and lock instructions. Note again that the result for the shared variable without the lock management could differ from the result shown. Let's recap. 1. Locks have two states, locked and unlocked. 2. We have two methods that are used to manipulate the locks, acquire parentheses and release parentheses. The following are the rules. 1. If the state is unlocked, a call to acquire parentheses changes the state to locked. If the state is locked, a call to acquire parentheses blocks until another thread calls release parentheses. 3. If the state is unlocked, a call to release parentheses raises a runtime error exception. 4. If the state is locked, a call to release parentheses changes the state to unlocked. Despite their theoretical smooth running, the locks are not only subject to harmful situations of deadlock, but also have many other negative aspects for the application as a whole. This is a conservative approach which, by its nature, often introduces unnecessary overhead. It also limits the scalability of the code and its readability. Furthermore, the use of a lock is decidedly in conflict with the possible need to impose the priority of access to the memory shared by the various processes. Finally, from a practical point of view, an application containing a lock presents considerable difficulties when searching for errors or debugging. In conclusion, it would be appropriate to use alternative methods to ensure synchronized access to shared memory and avoid race conditions. So in this video, we saw thread synchronization with lock. In the next video, we'll go through thread synchronization with rlock.